Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In the last video, we introduced the term entropy. In this video, we're going to discuss the entropy change for a chemical reaction. Now, we're still going to use a lot of the information that we gathered from the last video, such as an entropy change from a liquid to a gas is much larger than the entropy change from a solid to a liquid. And as we increase as we increase temperature, entropy increases. We're going to be using a lot of that information that we gathered from the last video to talk about the entropy change of chemical reactions. And I have 4 chemical reactions over here. And what we're going to do is we're going to predict if the entropy change is going to be positive, which means it's going to create more disorder as the chemical reaction takes place, because entropy is a measure of disorder, or if it's negative, okay? Now, if the entropy change is negative, that means the disorder is going down. And if the disorder is going down, that means it's getting organized, okay? And a lot of stuff that we're going to use is this idea of solid, liquids, and gases. So let's take a look at our first example, okay? Our first example is water in the liquid phase changing to water in the gas phase. And if we look at some of the stuff from our last video, if you go from a liquid to a gas, there is a humongous entropy change when that state change occurs. Because whenever you have those state changes, they're going to be really big. And going from liquid to gas is a bigger or a much larger entropy change than going from solid to liquid. So I'm going to predict that the change in entropy in this chemical reaction is going to be very positive, because we're going from liquid to gas, and that's going to be your largest jump in entropy that you can have. Okay, let's take a look at the next example. The next example is aqueous solutions. Okay, so an aqueous solution of silver ions and an aqueous solution of chloride ions are creating silver chloride in the solid form. Now, when we think of aqueous, we should be thinking that that's kind of like in the liquid state. So it's going to have a molecular arrangement that looks something like this. And in the chemical reaction, it's going to go from looking like this to this. And this looks really, really organized. So we're going to kind of go from solid to we're going to go from liquid to solid, which would be a decrease in entropy. So over here, because we got these state changes that are taking place, it's not going to be quite as large as liquid to gas. It's going from like liquid to solid, but it's going to be negative. I'm going to put 2 negative signs down instead of 3 positive signs, because the state change is liquid to solid versus liquid to gas. Okay, so remember, this one is going to be much larger than this one. Okay, so yes, it's going to go down, but it's not going to go down as much as the other one went up, if that makes sense. Okay, let's take a look at our third one. Okay, so our third one, we have 4 irons and 3 oxygens, making 2 iron oxides, or what we call ferric oxide. But let's take a look at the states of matter. This is going from solid to solid, so that might just be a wash. Now, remember, molar mass has a contributing factor. So going from this solid to this solid, there's more molar mass over here. So we're going to have a slight entropy increase if we go from, iron to iron oxide, okay? However, if we take a look at we got gas molecules over here on the reactant side, and this is going to be your major indicator. You are going from gas to solid when this chemical reaction takes place. So it's like going from right here as a gas to down here. You not only have this jump down, but you also have this jump down. This is going to be a serious decrease in entropy. Okay, so I'm going to load this up with negative signs. You got a humongous, not just gas to liquid, but you're going gas down all the way down to solid. That thing's going to get really, really organized. You're going to have something that looks like this versus this. Okay, that thing's going to definitely decrease in its disorder or number of microstates, okay, and become organized. Okay, so this is a big decrease in entropy change. Okay, now this last one, everything's a gas. Okay, we had gas molecules here and we got gas molecules here. okay? So when everything's the same state of matter, okay, I have a feeling this entropy change is going to be small, but we have to go a little bit further. It's not just, states of matter like the previous three were, okay? Now, the thing that I want to analyze for this last problem, okay, is the idea of how many gas molecules I have on each side. I got 4 gas molecules on the left-hand side and only 2 gas molecules on the right-hand side. So when everything is the same state of matter, okay, what you can look at is the number of molecules on both sides, okay? And the more molecules you have, the more disorder there's going to be. So on the left-hand side, I got 4 molecules, okay? And then on the right-hand side, I only have 2, so that's going to be organization. That's not an increase in disorder, that's a decrease in disorder, but I'm just going to give it a negative sign for that.